and they're both on bonding. So the concept of the chemical bond is so broad and complicated sometimes. It's going to take 2 chapters and 2 exams to cover the topics adequately. So chapter 8 is just general concepts of bonding. We'll start off with the concept of the ionic bond and then gradually move into covalent bonding and then theories about bonding, explanations for why bonds form. Okay. So what's meant by the term chemical bond? The chemical bond has been a mystery for centuries, actually. But everything that happens in chemistry revolves around the chemical bond. So understanding the chemical bond is absolutely essential to an understanding of why certain things happen when substances change their identities. One obvious question is, why do atoms bond with each other to form compounds? The other is, how do they bond to form compounds? Dalton's atomic theory made an initial step and sort of laid the foundation for understanding the nature of the chemical bond. But it didn't actually explain what drives atoms to associate with one another and why they arrange and rearrange. So that's what, in the past couple of centuries, that's what we've been focusing on. Unfortunately, there's no simple answer to it yet. In its most basic form, we can define the chemical bond as forces that hold groups of atoms together so that they act as a single unit. One thing we have been able to determine is that when you have, let's focus in on one type of reaction where you have an element plus an element, and it forms some kind of a bond. This element bonds with that element, say that atom bonds with that atom to make this compound. What we do know is that the combined energies of the reactants compared to, reactants and energy of the products is such that the energy of the products are always lower than the energy of the reactants. We know that for sure. So what that tells us is that one of the driving forces of a chemical reaction is for the reactants are trying to somehow attain a lower energy state. Lower energy always means more stability. Okay, if we're looking at a very simple explanation for why ions bond to one another. So we're talking about the ionic bond. There are 2 things that determine the strength of that bond. And these are better understood than some other explanations. When you have a positive ion and a negative ion, you know there's going to be an attractive force. So our example here is sodium chloride. So what you want to focus on is the strength of the charge. How big is the charge? So single charge, double charge is bigger than single charge. And how close do their centers of charge get to each other? They might have physics in here. Or you understand the term center of gravity? It's the point in an object that is apparently the center of all the mass of the object. So my center of gravity would be somewhere right around in here, inside. And you can use that simplification of my form to determine whether I'm going to tip over if I lean too far, because my center of gravity, once it exceeds my point of contact, I'll fall over. Well, in an analogous description of charges, you can think of them as a center of charge for this ion would be basically inside the nucleus. So the center of its charge, the sodium would be one positive charge centered at this point, and chlorine would be centered at this point, and the distance between them is an important factor in determining the strength of that bond. And the closer the charges get together, the stronger the force. Just like planets. Two things determine the strength of gravity, right? How big is the object and how far is it away from you? So if we were, well, on the surface of the Earth, I'm about 200 pounds, right? But if I go to the moon is smaller, plus I'm closer to its center. And there, I'm only about a sixth of that. Right? What, 33 pounds or so. So the same concept works for understanding the ionic bond. How big are the charges and how close are they together? And this is based upon Coulomb's law. There's Coulomb's law, right? You have that, you have this constant here, it's a proportionality constant. Sometimes we call them fudge factors. It's just saying that if energy is proportional to the charges times each other, so for sodium and chlorine, it'll be a +1 and a -1. And then, so the bigger these are, the stronger the force. But the closer they are together, the smaller this R value, also the stronger the force. Remember, when the number is in the denominator, if it gets smaller, then the quotient gets bigger. So that's all Coulomb's law is saying. And you can calculate the energy of that bond from an ionic standpoint. So if the value is negative, you know it's an attractive force. If the value is positive, you know it's a repulsive force. So in this case, it's negative. That means that sodium ion and chloride ion attract one another. So the bond for ions can be calculated. This bond strength can be calculated based upon the size of the charge, pluses, minuses, 2 pluses, 2 minuses, whatever the case may be, and the distance between them. So this is fairly well understood. Let's see, there we go. But when you get two like atoms approaching one another, you can't explain, well, if they're neutral atoms, they technically don't have any repulsive forces. But when you get atoms approaching one another, if they're exactly like, in this case, the two hydrogen atoms, right? They have one proton in the nucleus and one electron. So as they approach, what are they going to see first? They're going to see electrons. So initially, there's a repulsive force because those electrons repel. And then as you get closer, the positive nucleus repels also. But there's a happy medium where you get together. And as they approach, you got several forces acting, some of them for and some of them against bonding. But since they're not ions, we can't explain it in terms of electrostatic attraction. So what you get is these electrons are shared between the two hydrogens, and they give the hydrogen the feeling, the sense that it has a complete orbital. Right? The 1s orbital now has 2 electrons, or so each hydrogen thinks. And you get that model. You get the model here, where the electrons spend most of their time between the 2 protons. Right? And remember, this is just probability. This is not saying exactly where things are. Okay, so on balance, you have the repulsive forces of the 2 protons and the 2 electrons, and then you have the attractive forces of the electrons attracting the protons from either side. And what you get, if you diagram the forces that are involved, you find that actually you diagram the potential energy versus the distance between them. And the best way to look at this diagram is to go from right to left. So here the hydrogens are very far apart. And as they get closer to one another, their overall energies decrease until they get down to this particular distance, 0.074 nanometers. Right, or 7.4 angstroms. But if you try to push them closer, their energy goes up like that, way up. So there's a happy medium here, a distance between them which is ideal. And that's where the bond forms. So if you try to push them closer, which is what happens in a nuclear reaction, when you push them closer, before you can get to the point where the nuclei start to interact, you've got to overcome these massive repulsive forces. They don't like it. They don't want to get closer than 0.074 nanometers. So that's why nuclear reactions occur at very high pressures and very high energies, like at the center of a star. Or we've managed to do it in certain machines here on Earth, but not to any great extent. Okay. Okay, key concepts. Ionic bonding, electrons are always transferred from one to the other, and then the forces that are holding them together are purely electrostatic. Then you have the covalent bonding, where you're sharing electrons. And the nuclei are under the impression that hydrogen thinks it's a helium. Right? It's got 2 electrons now in counting the bond. Each one thinks it's a helium, but it's really not. It just lowers their overall energy. But bonds are rarely characterized as purely ionic or purely covalent, 100%, one way or the other. They're usually in between somewhere. Sometimes they're way, way over close to the ionic, and sometimes they're way over close to the covalent. So there's a continuum in between. All bonds, nearly all bonds, have some ionic character and some covalent character. So that's the first major concept. So how do we characterize them? Well, if we say that on this continuum of character, say we have ionic on this side, purely ionic, 100%. And on this side, we have 100% covalent, sharing only, no ionic character whatsoever. Then we have, within this, we can have covalent bonds, but as we move closer to the ionic side, we get one atom is a stronger pull on electrons than the other one. We talked about electronegativity, haven't we? No, maybe that's the second semester. Hold on a second. My outline. I get courses confused. Yeah, atomic structure and periodicity. We talked about that. You should have agreed with me. So we know about electronegativity. The more electronegative atoms are way up here, and the less electronegative are down below, right? Lower left, upper right, we increase electronegativity. So when you get two atoms together forming a bond, the one that's more electronegative will tend to draw electrons toward itself. So even though it's a covalent bond, it might be polar in nature. It may give it a slightly positive or negative on one side and positive on the other. But until you get to that point, we have sort of categorized this group here as non-polar covalent. All right. They're roughly equally sharing electrons. And we say it results in no charge separation, but it results in very little charge separation. In fact, this probably ought to be moved closer to the other side, maybe down here, like that. Then there's the polar covalent. Whatever region is in here, polar covalent. And in this region of covalent ionic character, you get enough pull from one side to give it a slightly negative character on this side and a slightly positive charge on that side. So these are said to be polar bonds, and sometimes we mark them like this. This is the positive side, this is the negative side. So that designates a polar bond. Resulting in a charge separation. It's not a complete ionic bond. It's still a covalent bond, but it has a negative character this way and a positive character that way. And we can measure. We can actually measure the difference. The example here is the bond between hydrogen and fluorine. Right? Fluorine is the most electronegative element in the table. And hydrogen is in the neighborhood of maybe 2.3, 2.4 electronegativity units. This one's about 4, and this is about 2.3, I think. So we get an uneven distribution, and you can measure that between these two plates. How much charge does it take to line them up? Right? And there are formulas that you can use and calculate that polarity of the bond. Okay, this is just rehashing. Why do atoms bond with each other to form molecules? Well, for lack of a better explanation, they bond because their overall energy decreases. They become more stable. And atoms will bond with each other either by sharing electrons or by transferring electrons to produce an ionic bond. I'm going to leave that up there for a second. Might use it again. Okay, electronegativity. I thought we had talked about this before. Because we covered a chapter on atomic structure and periodicity. No, we didn't talk about electronegativity, did we? No, we just talked about ionization energy, electron affinity, and atomic size. Okay, so we're going to add another one. We're going to add another one to the periodicity trends in the table. It's called electronegativity. And it's an expression of how strongly an atom draws electrons to itself. It was first proposed by Berzelius in 1811 and studied by other chemists ever since. There have been many attempts at a quantitative description of this character of atoms, but most chemists will settle upon Linus Pauling's scale, which he proposed in 1932. And it has a mathematical basis, but I think, well, for a number of different reasons, his system is used by most chemists, in large part because he actually, throughout history, at least for the sciences, most scientists tend to tear things apart and see what the little pieces look like and characterize this little bailiwick over here and this little one over here. Occasionally, rarely, you get a scientist who sees all these disparate parts, draws them together into a single coherent doctrine, if you will. Linus Pauling was one of those. In fact, he wrote a book on it called The Nature of the Chemical Bond. And in fact, the Nobel Prize Committee in Chemistry said, yeah, it's good enough for a prize. So he got a Nobel Prize for it in 1954. Because he drew all these different areas together and gave a reasonably coherent description of the chemical bond at that time. And some of his work centered upon this characteristic of polarity in a bond. And he set up a system where you could assign a number to each one of the elements based upon the strength of attraction that it held for atoms. And this was always in reference to how strongly did it attract in a bond, not just out by itself floating around. So it had to be in a bond in order to determine this value. And there's his formula. You don't have to remember the formula. It's just an illustration. If we bond an element to hydrogen, for instance, then what we're going to do is we're going to compare the expected bond energy of the HX bond, this some other element, by taking the bond of an HH and an XX. We can determine the strength of these bonds. And we add them together and divide by 2, and that's what we would expect the bond to be for this one. And then we measure the bond for that one. And if we take the actual for this one, the actual bond energy for this one, and we subtract the expected bond energy for that one, based upon this calculation that we just did, then you get a number. If the actual and the expected are exactly equal, then the difference is 0. Okay, and I don't know of any that are exactly 0. Cesium is way down around 0.2, something like that. It's very small. So the trend in the periodic table is that electronegativities, this calculated value, increases from lower left to upper right. That means that in a group, it will increase up the group like this. It'll be a greater electronegativity up this way. The reason for that is that the atom's getting smaller. Even though you're getting, you have fewer protons, the bond that can form a lot closer. So that factor overwhelms the difference in charge. if you go from left to right, it's also increasing in electronegativity. And that's due to the effective nuclear charge. In other words, from left to right, you're in the same period. So as you're adding protons to the nucleus, you're adding electrons, but the electrons are in the same energy level as you're adding those electrons. So there's no added shielding from the negative charges, so you get the increase in positive charges from the nucleus, and that increases its pull on electrons. In fact, the electrons that are there, as you add them, they actually move closer to the nucleus because you're adding more protons. So overall, let's see, I was wrong. Cesium is about 0.7, and fluorine is about 4, or exactly 4. So from 0.7 lower left to 4 upper right, you get an increase in electronegativity. Now, how do we use that? Well, if we have two atoms together, let's just take those for example. Say we have a bond between fluorine and cesium, right? Where fluorine is 4 and cesium is 0.7. Then if you subtract them, you get a 3.3. That's a very big difference. That would be very close to 100% ionic bond. If it's a very small number, then you're over closer to this thing. So the difference in electronegativity decreases this way. Actually, it increases that way, decreases this way. This is smaller, this is larger. Now, this trend works pretty well for the representative elements. Those right here in these two columns, and these over here in the last 6. Okay. So you gradually see an increase over here, and then you skip over the transition elements, and it gets bigger and bigger and bigger here. In the transition elements, you sort of get a roller coaster. You go up and then back down here. So they don't hold to the trend as well as the representative elements. Okay, so if we have lithium and fluorine react, which has more attraction for an electron? Well, lithium is what, way over there? Fluorine is way over here. So fluorine would have the stronger attraction. If a bond between fluorine and iodine occurs, which would have more attraction? Well, now we're in the same group. So if we've got iodine here and fluorine there, then fluorine is going to have the stronger attraction. And you can form bonds between two halogens, two different halogens actually. So fluorine is still going to have the stronger attraction. Okay. So here's the slide. Here are the slides on the explanation for why. I sort of jumped the gun. So explain the trends. Across a period, the number of protons increases the effective nuclear charge, which draws electrons closer to it. And in a group, if you go down in a group, you decrease the electronegativity, primarily because you're adding electrons to outer energy levels. Even though you're adding protons in the nucleus, you still got all these core electrons here that are shielding that positive charge from the externals, from the bonding species. So you're decreasing the effective nuclear charge as you move down a group. So here's an attempt at quantifying these regions. So if we go from the difference in electronegativity here, from say 0 here to 0.2, then we're still in the nonpolar range, nonpolar covalent. If we go from 0.3 up to, 1.4? Now we're going to call that polar covalent. And anything above this one, anything greater than 1.4, we call ionic. Or greater, 1.5 or greater. Now, there's a gray area in here. If you've got two nonmetals, this is 3 here. If you've got two nonmetals that are bound and give you a value in here, you can call it polar covalent. Nonmetal, nonmetal. If you've got a metal and a nonmetal bond together, and they usually have a value in this range right here. They won't have something over here. In this range, at this point, if it's a metal nonmetal, then even if it's less than 1.5, you're going to call it ionic. Okay, so let's see if we can organize these guys. Let me make some room. Arrange these from most to least polar. Right, so we have NF, OF, and CF. NF, OF, and CF. The way to approach this is to say, how far apart are they in the periodic table? Okay. Fortunately, fluorine is part of each one of them. So we find the one that is the most polar would be the one that's farthest away from fluorine. That would be carbon. Right? So this one would be more polar than the next one. And that would be more polar than the next one. Just like that. Simply because of their distance from each other in the table. Okay. The second one is a little trickier. This was A, B. Right, so the second one we have, say CF, NO, and silicon and fluorine. Okay, these were all in the same period. They were easy, but these, that's in the same period. NO is very close to nitrogen, is close to oxygen. This one is probably going to be the least. And carbon and fluorine would be in the middle, and silicon and fluorine are even further apart than carbon and fluorine. So it should be silicon, carbon, and nitrogen. Okay. Oops. Okay. How about the next one? C. So we got chlorine and chlorine, boron and chlorine, and sulfur and chlorine. All right, this one's going to be the least. It's not even going to be polar. It's going to be, because you've got the same element on either side of the bond. So if we had to include it, I wouldn't even include it because it's not even polar. But just to be complete, how far apart are boron and chlorine? They're pretty far apart. How about sulfur and chlorine? Sulfur and chlorine are very close. So they would be the next ones. And then boron and chlorine would be the furthest apart. Okay. So that gives you a feel for how to use this trend to get some idea about polarity of covalent bonds. Okay, if we have magnesium and oxygen, carbon and oxygen, 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 oh, they're all bound to oxygen, silicon and nitrogen. Which would be the least polar, but still be considered polar covalent? All right, so let's eliminate the ones that are not, that cannot be polar, right? Oxygen, oxygen, right? Can't use that one. Magnesium and oxygen. Can't use that one. That's ionic. It's a metal and a non-metal. Okay. So what do we got left? We got carbon, oxygen, and we've got silicon, silicon and oxygen, and we've got nitrogen and oxygen. So the least polar is going to be the one that's closest to each other, and it's probably nitrogen oxygen. Yep. Okay. Now you can do that. I did that by just general trends, but we did produce this. We did produce this table of electronegativity, so you could actually calculate the values. Let's see. Did I do right on magnesium, oxygen? Magnesium is 1.2 and oxygen is 3.5. Yeah, that's ionic. It's greater than 1.5. So we were justified in getting rid of that one because it's not covalent. How about this one? Most polar. All right, so we can still get rid of magnesium, oxygen, and oxygen, but the one that's most polar would be the one where they're farthest apart. Silicon and oxygen. They're the farthest apart in the table. Whoops. Most polar. No, I don't think so. I think that may be a mistake. Let's check it. Silicon is 1.8 and oxygen is 3.5. All right, so we got 1.7 for that one. And carbon and oxygen would be 2.5 for carbon, and oxygen is still 3.5. Okay, so that's an error. That's wrong.
It says without being considered ionic, the silicon and oxygen can put better.
Yeah, I guess, okay. Even though silicon is on the non-polar side. Okay, you got me there. All right. Okay, so we'll give them carbon, oxygen then. All right. So this polarity of a bond has a name. It's called the dipole moment, and that's derived. That term "moment" is derived from physics, and it has to do with directed forces. So there's a moment or a force directed in a certain, in this case, between atoms, and it produces an unequal distribution of electron density, which gives you a slight difference in charge. And we designate that. I showed you a little earlier. Let's see if we've got an example coming up. We can use this arrow, right, in which the positive end has a bar on the end of it. The negative end is toward the arrowhead. So we could have, say, something like this. We would say, yeah, its dipole moment is that way. And we could also give it a slight negative charge here and a slight positive charge there. This is the small Greek letter delta. And we used it for this purpose, throwing it to slight negative charge, not a complete charge. Now, how do we tell? This is just for bonds. We're interested in covalent molecules, like sort of water, for instance. Is water a polar molecule? Does the overall character of the molecule say that it's polar? Do you need two bits of information? to determine whether a molecule is polar or nonpolar. One is the bonds. If the bonds are polar, then you have a chance of having a polar molecule. If none of the bonds are polar, then the molecule cannot be polar. Right? So you just stop there and say, no, the whole molecule is not polar. For instance, if it's just a diatomic molecule, like two hydrogens, right? That's H2, that's definitely nonpolar. Or if you have gaseous nitrogen, that's nonpolar. But if you have polar bonds, say, well, for oxygen, water, excuse me. Water is shaped like this, and the bonds are polar toward the oxygen, like that. If this molecule, that's the actual shape of the molecule. If water were shaped like this, those two are equal and opposite in direction, they would cancel each other out. This would be a nonpolar molecule. So the two things you need to know are the polarity of the bond and the geometry of the molecule. That should be coming up. Here we go. Yeah. So that's what we're looking at now. We've talked a good bit about the polarity of the bonds. Now we need to get a handle on geometry. Okay, so have you ever heard of a concept called vector addition? Yeah. Linear addition, you're just in two dimensions, right? You say, if you move this far and then you're going to move 3 more units, 1, 2, 3, then you went that far. That's linear addition. Vector addition takes into account another dimension. Right? So in this case, we've got this one, this bond is polar that way and this way. So vector addition tells us that it's polar like that. Okay, it's the concept of physics. So that's why the water molecule is polar toward the oxygen. And there's one way of representing it there where you have red on this side, designating increased electron density, and on this side, decreased electron density. Carbon dioxide, that's not a good representation of carbon dioxide, because carbon dioxide has a double bond here, and a double bond there. It's still polar this way and polar this way on those bonds, but when you vector addition, add them together, you get nonpolar. They're equal and opposite, they cancel each other out. Okay. Other shapes that are possible for molecules. You could have a linear shape where you have 3 atoms in a row. You could have a trigonal planar shape. Let's see. Example. Boron trihydride is trigonal planar. In other words, if you imaginary connection around its perimeter, you get an isosceles triangle. And it's all in the same plane. Trigonal planar. If you have something like methane, methane, you have a hydrogen here, a hydrogen here, a hydrogen there, and then one in the back. So you get this trigonal base, and then if you connect the rest of them, you get a tetrahedron. That's a regular geometric shape for 4 corners. Okay. There are other shapes, and we'll cover them as needs be. But the idea here is if you know the shape and you know the polarity of the bonds, then you can make a prediction about whether or not the molecule is polar. Okay. Speaking of stability of compounds, in most cases, stable compounds are those in which the elements, I'm going to anthropomorphize, elements think they have an octet. So that's why oxygen tends to have a -2 charge when it's in an ionic compound. Right? It needs 2 more electrons. Add 1, add 2. It looks like neon now. Or for potassium. Potassium, if it loses an electron, then it looks like argon. So that's one of the driving forces, is that the elements tend toward, electronically speaking, looking like noble gases. And for all of them except for hydrogen, that's an octet. Hydrogen, of course, tends toward the duet. And this works really well for second and third period, these two, because and potassium and calcium work also. But once you start, and once you get into here, you're into, you're out of S and P orbitals and you're into D orbitals. And then the octet game is shot. Okay. So 10 forms 2+ and 4+ ions. We did electron configurations, didn't we? I know we did when we were doing trends earlier. Okay. So 10, if we take 10, which has 50 electrons, and we use our abbreviated version, so we go back to krypton for 36. This would be our essentially the core. Okay, now we have 14 more electrons. Okay, from krypton, we would have, let's see, 1, 2, 3, 4, 5, 6. We would have 6s2. That would take us past rubidium and strontium. And then we would have 5d10. That would take us across the transition elements. And then we get to indium and 10. And they would be 6p2. Okay, the reason that 10 tends toward +2 or +4 is if it loses these 2 electrons, right, it's +2. Okay, if it loses those 2 and these 2, it becomes +4. And then it's krypton plus 5d, which is a full, 5d is a full orbital. So that explains why 10 tends toward +2 or +4 charges when it forms compounds. We can do the same thing about lead, right? Lead is just 1 down, so it's going to have a similar format, only now it's 7, 6, and 7 with a different, of course, a different core there. That would be xenon. Bismuth, right? Where's bismuth? Right here, to the right. So now bismuth would have 6d10, 7s2, and 6p3. So if it lost these 3, that makes it a +3. And if it lost 2 more, it makes it a +5. So bismuth prefers either a +5 or a +3 charge. Okay. If that flickering gets to you, you're welcome to turn around and look at the other screen. Thallium, where's thallium? Tl, right here. So it only has 1 p electron, but it still has 2 s electrons. So lose 1, it's a +1. Lose 2 more, it's a +3. That gives an explanation for why these ions are preferred for each of these elements. Okay. Generally speaking, when two nonmetals get together, they form covalent bonds because their electronegativities are not big enough or not large enough relative to one another for one of them to win out and become an ion, and a negative ion and the other one a positive ion. So they tend to form covalent bonds. Whereas metals and nonmetals are far enough apart usually that one of them, the metal, wants to lose electrons and the nonmetal wants to gain electrons. So it just gives them up and the nonmetal gets them, and we have two opposite charges, electrostatic attraction. And when they do that, they tend toward forming the electronic configuration of noble gas. They're isoelectronic with noble gases. And as an example, here's a series, an isoelectronic series. If oxygen loses 2 electrons, it looks like what? Not gains 2 electrons, excuse me. It looks like neon. If fluorine gains an electron, it looks like neon. Neon is just neon, but they have the same electronic configuration. Sodium loses 1, it looks like neon. Magnesium loses 2, looks like neon. Aluminum loses 3, it looks like neon, electronically speaking. Those are isoelectronic series. There's another one. I'm not going to beat that horse anymore. Those are electronic. That is an electronic series, isoelectronic series. So the configuration looks like that. Notice it's complete. Right? Every orbital is full. S's have 2s, P's have 6s, all the way across. The number of electrons is exactly equal, 18. Number of protons is still different, right? Because they're different elements. Right? You can't change the protons unless you want to change the element. All right. Okay. So we've looked at differences in atomic size. We mentioned something about ionic radius. I don't know if it was in the PowerPoint slides or if it was in the review document, but we did discuss a little bit about ionic radius. If you add electrons, of course, the ionic radius is going to balloon. If you subtract electrons, it's going to shrink. Ionization energy, we talked about that. We know how to draw an electronic configuration. We know how to draw ionic compounds, write ionic compounds, and balance the charges for the compound. And now we know something about covalent bond polarity. So, say you have a solid binary ionic compound. The strength of attraction is given a name. It's called lattice energy. Lattice energy actually is defined by a formula. If you have and this could be a multiple charge, it could be 2, 3, or 4 plus. And you bring it together with an anion, a cation and anion, these have to be gases. When they come together and they form a solid from that, they're going to give up energy. Right? This is high energy side, this is low energy side. So they're going to give up energy. This is exothermic. And the amount of energy they give up, which would be a negative value, the more negative, the more energy they give up. That is a measure of the lattice energy. And the reason we call it lattice energy is because when ionic compounds form, they don't just form one ion against another ion. They form associations of cations and anions in a matrix, in a lattice. Okay. Now, the lattice energy can be calculated, right? And that's a takeoff on Coulomb's law. It does have a different proportionality constant, though, right? This value is going to be different, but it's a similar concept, right? The size of the charge, the distance between them, and then our proportionality constant, which makes this equal to joules in some form or fashion. Now, that's the lattice energy. The overall energy of a reaction can be broken down into these steps. So if you have a metal and a non-metal, right? We're talking about ionic bonding now. If you have a metal and a non-metal, then they go through certain steps to get there. It's kind of like that, we talk about solutions yet, right? Let me see. Gases, stoichiometry, types of reactions. I think we did talk about solutions, where when you have the solute and the solvent, the first two steps are you bust this one apart, add energy, and then you bust this one apart, make a hole. Remember that? Yeah. And once you get them apart, then when you put them together, the solute interacts with the solvent and forms a bond. So you get some energy back. So the balance of that energy put in and the energy you get back determines whether the overall reaction is endothermic or exothermic. So those cold packs and hot packs you can get at the hospital, when the solid goes into solution, if it takes a lot of energy to get those things busted apart and you don't get much back, that's a cold pack because it drew energy from the surroundings. But if it takes a little bit of energy to get them apart, and then you get a whole lot of energy back when they reform their bonds in solution, then that's a hot pack. Okay, exothermic. Okay, similar concept here. When you're trying to bond a metal with a non-metal, they go through steps. The first step is we add energy and convert the metal from a solid, and that includes everything except mercury, because mercury is a liquid. But the energy required to go from its normal state to a gas is endothermic. You put energy in, okay, you get those atoms separated. And then ionization energy says, okay, we strip electrons off of it. And so we're familiar with this one right here. That's the ionization energy. This is the sublimation energy for a solid. Get the solid to go to a gas and then take the gas and strip an electron off of it. Then you go to the non-metal. What do you do with the non-metal? Well, the non-metal, you have to, in this example, you have a diatomic, like hydrogen, and you need to break the bonds, right? You got to get the atoms separated. Non-metals very often are covalently bound to their neighbors. And then you form an ion from that. In other words, they attract an electron to themselves, right? The neutral gas attracts an electron, and that's called what? Electron affinity. So the electron affinity here is the value that would be associated with that exothermic process. And then once you've got the ions created, then they come together as gases and make a solid. That's your lattice energy. So we got all these different steps that have to take place in order to form this ionic compound. I think there's a chart here. I mean, that's really small amounts. But if we follow it from, oops, wrong direction. if we follow it along and we say, okay, here's the metal, and this takes a certain amount of, let's see, no, that's a compound, and this is a compound. They're two different compounds. So let's stick to the left side. So if we take this, we're going to react magnesium and oxygen. And here we make magnesium into a gas, add energy to it. Then we ionize the magnesium. Come on, here we go. Ionize the magnesium here. Now we take the oxygen gas and we split it apart into oxygen atoms. And then we allow oxygen to attract electrons to itself. And then we go from there and we put these two gases together and make a solid. That's the lattice energy. And this overall, once we put them all together, we get this amount of energy overall is given up in the reaction of magnesium, metal, and oxygen gas. So all those steps go together. All those steps go together to give us that overall energy change. And it's a decrease in energy. It's an exothermic process. So the product is more stable than the reactants. It has lower energy. I'm not going to look at the other ones, same concept. Okay. All right. Oh, I guess we're going to follow lithium fluoride along. So here's the overall reaction. We break the reaction up into pieces, right? So, come on, there we go. So first thing we're going to do is sublime lithium. We're going to make a gas out of it, and then we're going to strip an electron off of it. So those are both endothermic processes. And then we take the fluorine and we break it apart and allow an electron to attract to it. And then we bring those two gaseous ions together. That's the lattice energy, and we form the solid. And we put all those together, I think is on the next slide. Put all those together. The overall is minus 617 kilojoules per mole. Okay, and there's the math, step by step. Okay. So here, this slide speaks to the partial ionic character of covalent bonds. And what we're emphasizing here is that there's no bond that's 100% ionic character. All bonds have some covalent character. All covalent bonds have some ionic character. And if we want to quantify it, what we need is a calculated dipole moment for the bond versus a measured dipole moment for the bond. And then we can quantify the percent ionic character based upon that formula. Right. There. And if we do that, and we look at these diatomic molecules, then they can group them together. Percent ionic character is essentially forms a straight line with some deviation, a straight line relationship between electronegativity difference and percent ionic character. So the smaller the electronegativity difference, the smaller the ionic character. These are very close to covalent, purely covalent. And these up here are very closely associated with ionic character. Okay. Ionic compounds. There's, I remember when I was working on my PhD, one of my committee advisors, I was talking to him about a particular soil test that I was using, separating out manganese from the soil in various fractions, where it was located in the soil. And I asked him, how do I characterize these tests for the benefit of my committee when I go for examination? And he says, your tests, your soil tests are operationally defined, which just means they're whatever you want them to be. So we have an operational definition here for an ionic compound. Any compound that conducts electric current when it's either melted or it's in solution is an ionic compound. So if you can put it in solution, in aqueous solutions, for instance, put sodium chloride, we know that's an ionic compound because it will conduct electricity. Or if you melt sodium chloride, believe it or not, you can melt salt if you get it hot enough. Now, why will it not conduct electricity when it's in crystalline form? Right? There's a sodium chloride crystal. You may have a sodium here, you have a chlorine there, you have a sodium here, and chlorine there. In that crystal structure, those ions are locked into place. They cannot move. So they cannot conduct electricity. In order to conduct electricity, you have to have mobile charges, right? In a wire, the mobile charge, of course, is the electron. But in solutions or in melted substances, you have to have mobile ions. So if you do that to them and they still don't conduct electricity, then it's not ionic. Okay, you can have some covalent compounds that you can melt and they still won't conduct electricity. For instance, wax, right? You ever used a wax bath for arthritic pain? It works. You have paraffin in this bath and it's heated and you dip your hand into it and pull it out. And the heat from that wax, as it solidifies and cools, sends heat into your joint and gives you relief. But when you melt that paraffin, if you stick two electrodes into it connected to a battery and a light, no light. It will not conduct electricity. So that paraffin is, by definition, a covalent compound. Okay, now we're going to talk about models. Remember, laws just tell you what happened. What happens? If you know the parameters and you know the law, then you can predict an outcome, but only for the narrow range of parameters that are accessible to that law. If, on the other hand, you have a theory, then you can explain, at least with a theory, as far as it's concerned, you can explain the why this happens. And you can explain an outcome, plus you can change parameters and predict different outcomes. And that's where the model comes in. Almost all theories have a model associated with it. Sometimes it's a physical model, something that you can build like a model airplane. Right? It's not the real thing, but it's a model and it gives you an idea of where things are located in the airplane and how they work to a certain extent. So models and theories go together. Right? We have several models that we use to describe chemical bonding. And since we can't actually see what's happening, the model is useful, even instructive, for us to understand how the bonding works. All right. So these are characteristics of any model, actually. First of all, you have to realize that a model is not reality. That's the first prime directive of models. The model is not reality. It's a representation of reality. Models, in fact, are oversimplifications. In other words, the less important factors we tend to leave out of the model because they complicate things. And we want things, scientists love simplicity. We call it elegant. If it's simple and explains a problem, then it's elegant. Unfortunately, as we progress and we learn more about the system that we're trying to model, the model tends to get more complicated. In other words, we tend to stick more factors in there. We tweak it to make it behave more like reality. So we want our models to look like reality. And that's just the nature of the beast. One thing you do need to know is what are the underlying assumptions in the model. And the reason for that is so that you don't misuse the model. Try to make the model do something that's not intended to do. All these climate models, perfect example. Every climate model, I don't know how many there are now, a couple of dozen climate models that are being used around the world. None of them work. They all fail, every one of them. They're trying to make their models do something that they're not designed to do. When a model is wrong, we can often learn much more from it than when it's right. If we can figure out what's wrong with our model, why doesn't it match reality, then that gives us an insight as to what is the real nature of the real world. So a failed model is not necessarily bad. Okay. Let's see. Okay, I'm glad I had this slide on there. What do we do when a model stops working? Right, we have choices. You can restrict its application. You can say, okay, outside of these parameters, this model does not work. So do not use it. Okay, and that's what happens to a great many models, except for ones that are anchored in politics. For instance, Newton's laws of motion. They are only good for classical situations, masses that are not too big and systems that are not too small, intermediate. Masses and velocities are not extreme, right? When you approach the speed of light, you can't use Newton anymore. Or when you approach the size of a black hole, Newton's laws fall apart. Or when you get real small, like the size of an atom or a proton or electron, Newton's laws don't work anymore. So we restrict its application, right? They still work on stuff that we can see right here. Like I throw a baseball, yeah, we know how it's going to work in a gravitational field. Or you can modify the model to accommodate new conditions, and that's what many models do. That's why they become more complex. For instance, there are some physicists that claim that in the real world out here, mathematically, we can describe the real world if you give us 26 dimensions, not just height, width, breadth, and width, depth, this way, that way, and this way, and time. So 4 dimensions is all I can wrap my mind around, but some physicists say, oh, no, we need more than that, 26 dimensions in our equations. So they complicated it so far that it doesn't make any sense, except to those scientists and their colleagues. Or the other possibility you have is to throw the model out, start over. Right? That happened with J.J. Thomson's plumb pudding model for the atom. Remember that one, where we had the atom, and he said, okay, I know there are negative charges coming out of there, right? So they're discrete. They're like little pieces of plum. But the positive charges are like this matrix, this gooey matrix in which we insert the negative charges. Rutherford came along and shot that one out of the water with his gold foil experiment. Now we know that atoms are nuclear based. So the plum pudding model just had to go away. There was no way to recover it. Okay. So what's a bond energy? Well, it's the amount of energy required to break the bond, right? To separate the atoms from one another to where they're no longer bonded. And these are endothermic processes. When you break a bond, you have to add energy. So it's going to be a positive value plus some number, kilojoules per mole. When you form the bond, then it's the reverse of breaking the bond. So if you can determine how much energy it took to break the bond, you just change the sign, and that's the amount of energy it takes to form the bond, is released when you form the bond. When you bring the atoms together and they form the bond, they will give up energy in the same amount as breaking the bond, only with opposite sign. All right, we can characterize bonds, and the only ones that I've ever known, I'm sure there are others, right? If you're in an advanced PhD degree, research for a degree in chemistry, maybe you know more than single, double, and triple bonds. But we represent the bonds as either single bond, and this is always 2 electrons. Or we could have a double bond. So that would be 2 here and 2 here. That'd be 4 electrons. Or we could have a triple bond. And that would be 2, 4, 6. Sorry, that's my phone. I forgot to turn on my silencer. There we go. So that's all that means. How many electrons do you have? Single bonds 2, double bonds 4, triple bonds 6 electrons, with 2 electrons for each bond. One other thing that we notice is that as you go from single, double, and triple, the distance between the atoms decreases. The bond strength increases, which draws those atoms closer together. So it takes more energy to break a triple bond than it does to break a double bond. And it takes more energy to break a double bond than it does a single bond. Now, it's not multiplicative. In other words, if it takes so much energy to break a single bond, it doesn't take twice as much to break a double or 3 times as much to break a triple. And hopefully we'll show you why as we work our way through this chapter and the next. But for now, that's good enough. And here are quantities that are associated with the different types of single and double and triple bonds. Right, those values are in kilojoules per mole of the bond. Yeah. So they don't have any signs on them. So it depends on how you use it. Are you using that much energy to break the bond, or are you getting that much energy back from the formation of the bond? So we don't put a sign on them in this table. So you would see that, say, with the hydrogen-hydrogen bond, it 432 kilojoules for every mole of that bond. Or it takes a little bit more if the bond is between hydrogen and fluorine. And then it goes down, it gets less and less and less for the hydrogen and the other halogens. And then you get double bonds over here, right? Oxygen-oxygen is 495. Let's see, we have a carbon-oxygen triple for 1,000. That's pretty high. We have a nitrogen-nitrogen. This would be like gaseous nitrogen, N2, 941 kilojoules. So it's a very strong bond. But notice if you have a nitrogen single bond, here we go, 160. What's 3 times 160? Be 3, 480, 480. So they're not linear. Actually, this triple bond is much, much stronger than the single nitrogen-nitrogen bond. Okay. We'll use those values later, but you don't have to memorize. So if you have a problem that you need to know the bond energies for individual bonds, it'll either be given to you in the problem or ask me, and I'll look it up, give it to you. But that table came straight out of your book. So if you need them, it's in your book. So the bond energy is the energy that you have to add to break the bond, or the energy that's released when the bond forms. Either way. Now, if we're calculating the change in enthalpy for a reaction, say you have something as simple as, say, hydrogen gas and oxygen gas react to form water, right? Talking about space shuttle engine, or a lot of rocket engines are like that now, hydrogen and oxygen together, and forms, let's say, a gas. All right, so if we balance this, we need 2 of those and 2 of these. Okay, now, can we calculate a change in enthalpy for that reaction? Yeah. What we have here? Well, we have 2 times this bond here. And we have 1 times that bond. And here we have 2 of these bonds. Yeah, that's right, 2 of those bonds. So what you do is you say, what's the energy required to break these bonds here? And then you subtract the energy that you get back from forming those bonds. Okay. So when you break the bonds, you have to add energy in, they're positive values. And then when you get energy back, when you get energy back, they're negative values. That's why the negative sign. So those values that you saw in that table, just consider them all positives, because the formula takes into account using this, well, there it is, takes into account that negative, takes into account the energy released. Okay, so you don't have to incorporate a sign on your own. It's in the formula. Okay, for instance, here we go. We've got the molecule on the left rearranges to the molecule on the right. So, it just did the calculation. All right, what do we got? We've got CH3 in triple bond carbon becomes CH3 carbon triple bond nitrogen. Okay. So this is the way we write organic compounds. When we write a CH3 here, that's like this one with hydrogens here, 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 and here. And this one is a single bond to the nitrogen. Okay, so that there's no confusion. That's the way we write them. The hydrogens belong to that carbon. So notice that we've got the same thing on both sides. At least for this part of the molecule, these 3 carbon hydrogens, Then we get this one to the carbon, and then that one over there, and this one right here. So we don't even have to consider these because they're the same on both sides, right? All we have to consider is this bond and that bond. Right, so we take the energy of this bond, 1 carbon nitrogen, 305. 1 nitrogen triple bond carbon. Well, that's the same on both sides, isn't it? This one and this one. I just flip them, it's the same bond. Right, so the carbon nitrogen, and the only one we have to interest ourselves on this side is the carbon carbon, 347 minus. So 305 with a plus there would be 2 4. It'd be minus 42 kilojoules per mole. Okay. We just made it easier because this one didn't change. And this one's the same. This one's the one that changed right here. All right. just using that formula. Okay, normally what I would do is we would pause here, and I'm way over anyway. Let's see. 350. Okay, does anybody need to take a break?
I do need to put my daughter.
Oh, well, you can watch the video later.
Okay.
Oh, remember we talked about determining the polarity of a molecule, right? We know how to determine whether the bonds are polar. Now we have a theory that allows us to predict the geometry of the molecule. And now we're talking about covalent molecules. We're not talking about ionics. This is purely covalent. The valence bond theory. All it says is that was based upon the overlap of atomic orbitals. In other words, when you get two atoms approaching one another, I don't know, carbon and carbon, they have orbitals and maybe orbitals like that. That's not good. And even figure eight. Yeah. So as they approach one another, these orbitals will overlap, but they still belong to each carbon. Right? The carbons have not given up their atomic orbitals. They just overlap and form the bond. Okay. But the ones that overlap are the ones that have valence electrons. In other words, they're the outermost orbitals that are responsible for bonding. That's the valence bond theory in a nutshell. What we derive from that is this model, the localized electron model. And it basically says that when the molecule forms, the atoms that are bound together, once they form this bond, they do so by sharing pairs of electrons, right? And you can have one electron from one side shared, right, form a bond, or you could have two electrons from one side shared by both atoms. I mean, after the bond forms, there's no way to tell where they came from. But it does take two electrons. There's more to it than that. We're getting there. What has informed the development of this model over the years is a theory called the quantum mechanical theory. And it's basically, not to get into too much detail, but it's a probabilistic model. It's mathematical. And it's taken decades to work out the kinks. But it's fairly successful in predicting various things like orbitals around atoms, how they interact when you start to form a bond. These are some of the major players. Heitler, London. Remember London dispersion forces? Oh, we haven't talked about that, have we? We haven't talked about that. I don't think so. Okay. Don't worry about that. Just put it back here somewhere. We'll get to it in the summer, I guess. Linus Pauling worked on it also. But they were just a handful of the major players. There were dozens and dozens of chemists working on this, physicists actually working on this quantum mechanical problem. Okay, here's the way the localized electron model works. And since it's a model, it's going to build up a picture of what the atom, the molecule looks like when the bonds form. Right. First of all, the electron pairs have to be assumed localized on a particular atom or a space between the atom. Right. So if we have two hydrogens come together, Each one has an electron, right? It can form a single bond by sharing those two electrons. But those electrons belong to each of the hydrogens. Okay, that's essential. For others like nitrogen, when nitrogen comes together, it forms a triple bond. But it also has some extra electrons that are not used. These are called bonding pairs, or these bonding pairs, 2, 4, 6. These are lone pairs. They're non-bonding electrons. Okay? And we have to consider each type, the bonding and the non-bonding, in order to make the model work. So they're all important. Okay. We're going to get into parts 1 and 2 in this chapter, and then we'll move to part 3 in the next chapter. So you only have to be concerned with the first 2. First of all, we're going to use I don't call it a trick, but it's a form of representing an atom and its electrons in such a way that it's easier to visualize how they bond when they come together. And it was developed by a brilliant chemist, G.N. Lewis. And we call it the Lewis dot structure, the Lewis model. And he based his model upon this octet rule. So for the second period and the third period, all those elements, they tend toward an octet in their valence shell. So he said, okay, if they tend toward an octet, that means we should have 8 electrons for any of the noble gases in their valence shell. And everybody else, if they're deficient in electrons, they have less than 8, then what they're going to do when they bond is try to fill those missing places. Okay? Now, hydrogen, of course, would be a duet, not an octet. So we need to learn how to draw the Lewis dot structures for any of the atoms and any of the molecules too. And we'll do that. So this gives you the duet rule for hydrogen. So each hydrogen, because it's bonded like that, this one thinks it's got a helium structure. This one thinks it's got a helium structure because they're sharing those 2 electrons. So if it just looks at, if it's localized electrons, then that looks like helium. And that looks like helium. Fluorine would be, let's see. Well, that's how we represent a single bond with 1 dash. Double bonds have 2 dashes. There's a triple bond for nitrogen. 6 electrons means a triple bond. So how do we write the Lewis dot structure? Well, there are the rules, but I think it makes more sense if we just do some of them. So what you do is, well, before we get to the molecules, let's do an atom. So say carbon. There's carbon. How many valence electrons does carbon have? Count from the left. 1, 2, 3, 4. It has 4 valence electrons. Right? 1, 2, 3, 4. That's how you would draw carbon in the Lewis dot structure. How about fluorine? Okay. How many valence electrons does fluorine have? We'll count over from the left. 1, 2, 3, 4, 5, 6, 7. It has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. With 1, these are paired. This is unpaired. Okay. That's how you would draw the Lewis dot structure for any of the elements. Now we want to draw for Lewis dot structures for molecules. So the way you do it is you have the formula. You've got to have the formula for the molecule. Then you say, okay, how many electrons does each atom contribute? Well, there's 1 here times 2. right? So 2 for the hydrogens, and oxygen has 1, 2, 3, 4, 5, 6. 6 electrons. So that's 8 valence electrons. Okay? Now you take the central atom, which is usually the most electronegative one, goes in the center, and you form a single bond between it and the other atoms. Like that, like that. So you've used up 2, 4. You've used up 4 electrons. So you have 4 electrons left. Now to position the 4 electrons, you work from the outside in. Right? Hydrogen can't take any more. It's got its duet. It's got 2 here, 2 here. Right? So you can't go to hydrogen. We move in. Oxygen. Oxygen gets those 4 electrons. There and there. Like that. So that would be a representation of the water molecule in Lewis dot structure. Well, I went ahead and gave it its geometry. What we would do is just put hydrogen on this side and hydrogen on that side like they did up there, and then position the electrons, position the electrons okay, that's right. Yeah. So what else do we have as examples? Let's try and make one of them. How about PBr3? Okay. How many valence electrons do we have? Phosphorus is 5. And each one of the bromines is 7. So that's 21 plus 5, it's 26. 26 electrons. Okay. Phosphorus, in this case, phosphorus goes in the middle. Sometimes it follows that electronegativity rule, sometimes it doesn't. So we got 1, 2, 3 for our bromines. 2, 4, 6 minus 6 equals 20. 20 electrons. Okay, so you start merry-go-round. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? 2, 4, 6, 8. Bromine's got an octet now. And we got 2 more left, don't we? 2 electrons. So where do they go? They go on the phosphorus. Right there. That would be a valid Lewis dot structure for this one. And 2, 4, 6, 8. Phosphorus has an octet also. Okay. Let's see. There we go. When we do hydrogen cyanide, maybe we better do that. So you can see how it got to be that way. So there's 1, there's 4, and there's 5. Right? So there's 10 electrons. We have carbon, nitrogen, hydrogen. Okay, so that's 2, 4. 6 electrons left. So start from the outside and work our way in. 2, 4, 6. Okay. Hydrogen's got a duet, nitrogen's got an octet, carbon got left out. So how can we preserve that octet and give carbon an octet? We move these 2 into a bond. We move these 2 into a bond. If we do that, and leave these 2 out here, we still have the same number of electrons, but now carbon has an octet, nitrogen has an octet, hydrogen has a duet. So that's a valid Lewis dot structure for hydrogen cyanide. All right. Okay. Now we're going to use these Lewis dot structures to say something about the geometry in just a minute. Come on. Huh. There we go. So the Lewis dot structures for these. How about ammonia? Let's just do ammonia. There we go. So nitrogen has 5, 3 hydrogens has 3, so that's 8 electrons. So you have nitrogen with hydrogen, 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 2, 4, 6. So we got 2 electrons left. There's no room for them out here, so they have to go here. So that would be your valid Lewis dot structure for ammonia. Oops. Oh, it's not even going to show us. Okay. Sometimes, remember I said this before, nature just does what it does. We have to explain it. Here's a case. This compound, boron trihydride, is real. It does exist. If we try to draw a Lewis dot structure with 6 electrons, boron only has 6 electrons. It doesn't have an octet. It is deficient. These examples, sulfur tetrafluoride and arsenic pentabromide, have too many electrons, right? All the fluorines and all the bromines have their octets, but the central atom has to suck up extras. Sulfur and arsenic both exceed their octets. Now, how do they do that? Well, look where sulfur and arsenic are located on the periodic table. Sulfur's here. Right? 1, 2, 3. N equals 3. How many L's can you have? 0, 1, 2. S, P, D. Sulfur has access to d orbitals. Arsenic also has access to d orbitals. That's where those extra electrons go, into d orbitals. You don't see this excess electrons around the central atom unless it has access to d orbitals. Okay. Otherwise, you might get deficiencies, like boron. Boron is deficient. In that example I just gave you. Okay. Now, boron trifluoride is a different story. See, with the trihydride, the hydrogens only have 1 electron each, but the fluorines have lots of electrons. So we can draw a valid dot structure for boron trifluoride because we can access extra electrons from 1 fluorine and make a double there. So boron can have its octet. But is that the only way to write this one? No, we could have put the double bond here, or we could have put the double bond there. So you have 3 valid Lewis dot structures for boron trifluoride. We maybe only show 1 of them here. Yeah. Phosphorus pentachloride. Right? Phosphorus has got 10 electrons around it. Phosphorus, yeah, phosphorus is 3rd period. It does have access to d orbitals. And sulfur hexafluoride has 2, 4, 6, 8, 10, 12. Has 12 electrons, not just 8. Okay. Carbon, nitrogen, oxygen, fluorine always obey the octet rule. Boron and beryllium sometimes are deficient. 2nd row elements never exceed. So these never exceed the octet. But once you get to the 3rd row, you can exceed the octet because they have access to d orbitals. All right. So here's another example of multiple possible Lewis dot structures for a single molecule. In this case, it's polyatomic ion, nitrate. So this nitrate can have three possible structures, right? Depending on where you put the double bond. Well, this is one of the failings of the model. You have to write them that way with these whole bonds, singles, doubles, triples, whatever the case may be. And then the lone pair electrons placed where they are to make the octets. And of course, each one, since this is an ion, right here, then we have an ion there. We have to show the charge. If we don't show the charge, then we're not accounting for all the electrons. But this is one of those places where we have to tweak the model, right? How do we explain these three possibilities? They're equally valid Lewis dot structures. So we have to invoke something called resonance. We just say that these structures, they resonate among one another, backwards and forwards, so fast that we can't tell the difference anyway. What we do know is that for valid single, double, triple bonds, the single bond is a certain distance, double bond's closer, triple bond's closer. Every bond in this ion here, that one, and that one, they're all the same length. They are equal bonds. So our representation is not quite accurate. Right? They're somewhere in between single and double bonds. Sometimes I've seen it written this way. Like that. To show that they're all equal, but they're not quite double and they're not quite single. Something in between. But this is not a valid structure for this model. Using the Lewis dot structure, it's not valid, so we can't use that for this model. That's just one way of representing them. We have to fall back on a tweak, resonance. That's one of the failings of the model. Okay, I'm not going to draw those structures. There's plenty of practice in your review document, and we'll cover those when we do a review. Let's see, and I think the review for this is a week from today, is it not? Today's the 4th. Yeah, because Thursday's a buffer, so we can use that. Reviews next Tuesday. Just confirming in my own mind. Okay, how do we know if we have multiple Lewis dot structures? How do we know which one is preferable, or if they are all equal? There's a procedure called formal charge. Calculate formal charge in order to determine which is best. I'll just say this at the beginning. When we calculate the formal charge for each atom in the molecule, the lowest, the closest to zero that all of the atoms are in formal charge is the ideal. Okay. So how do we calculate formal charge? Well, you take the number of valence electrons that are assigned to each atom individually outside the, let's see, let's use water. Okay, water is going to be like this, like that, like that. Okay, what's the formal charge on each one of these? Well, how many valence electrons are assigned to each one on the periodic table? Right. Hydrogen's 1. Oxygen is 6, right? Okay. How many do they have in the molecule? Well, if it's a bond, they get one. Right, so they get one, it gets half of that one. This one gets one, this one gets one here. So 1, 2, 3, and lone pairs are assigned purely to the atom on which they're located. So oxygen gets both of these, 2, 4, 5, 6. Minus 6 equals 0. 1 minus 1 equals 0, minus 1 equals 0. So the formal charge on each one of these atoms is 0. That's perfect. Okay. Let's see, we've got some other examples. Those are just instructions. Come on. There we go. How about this one? POCl3. What's the formal charge on each one of these atoms? P, okay, single bond there, oxygen, Cl, 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 and each one of these has an octet. And oxygen has this one, this one, this one, like that. Okay? So we got octets all around. What's the formal charge on each one? Well, for all the chlorines, how many you got? Halogens have 7 assigned. How many do they have here? 1, 2, 3, 4, 5, 6, 7. Right? Minus 7, 0. So each one has a formal charge of 0. How about this oxygen? Well, oxygen has 6. 6 assigned. How many does it have here? 2, 4, 6, 7. Right? Half of that. So it has a formal charge of minus 1. And the phosphorus is 5. Right? So it has 5 electrons assigned. And how many does it have here? It's 1, 2, 3, 4. Plus 1. So all the chlorines have a formal charge of 0. Oxygen has a minus 1. Phosphorus has a plus 1. And since we can't draw any other form, there's no other way to draw this structure, then this is our choice. Did I lose you?
Yeah.
Okay.
How come was phosphorus one that had to obey the octet rule? The 8?
It doesn't have to, but it does in this case.
Okay.
Right? 2, 4, 6, 8. It has an octet.
Confused me at how you got like the 4.
Oh, I took half a bond. When there's a bond, the atom gets half of the.
You're just counting the bond and not the electrons.
I'm counting 1 electron for each bond. Right? The other electron goes over here. There's an electron here, an electron here. Electron here, electron here. Right? There are 2 electrons per bond. So this oxygen gets 1 of them, and this phosphorus gets the other one. So it gets 1 from here, 1 from here, 1 from here, 1 from here. That's 4.
Okay, that makes more sense.
Okay. But in the periodic table, it's assigned 5 valence electrons because of where it's located. So when we take 5 that it's assigned minus the 4 that it's given in the structure, it has a formal charge of plus 1. Right? And oxygen is assigned 6, but it has 7. 1, 2, 3, 4, 5, 6, 7. So it has a minus 1 formal charge. All right. That's a little different than the, what's that other one? Well, mine's gone blank. I'll think of it in a minute. Okay. There we go. All right. Oxidation state. When you calculate the oxidation state, it's a different set of rules. And it works under certain circumstances, but this works better for covalent compounds. And actually, oxidation, formal charge is peculiar for organic chemistry. And we just sort of use it in inorganic when we can. So the sum of all the formal charges in the atom must equal 0 for neutral molecules. So all the summation for this particular one we just did was 0, 0, 0, plus 1, minus 1, it's all 0. So there's no charge on the molecule. There's no excess charge left over from the summation of the formal charges. But if we did nitrate ion and added those formal charges up, they would have to be equal to minus 1 because NO3 minus has a charge. So here we have two possibilities, right? Carbon dioxide, we can draw these two structures. Right? We can draw this one or we can draw this one. And we've satisfied the octet rule in both cases. But which one is preferred? Well, if we do the formal charges for each one, we find that we get a lower overall formal charge for the atoms with double bond on both sides of the carbon rather than a triple and a single. Right, if we do, let's see, is it going to do that one? No, it's not. All right, so if we have this one, yeah, here, 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 here. So this one has 4, carbon has 4, oxygen has 6. So we have 1, 2, 3, 4 here. That's 0. We have 1, 2, 3, 4, 5, 6. 0 minus 6 equals 0. So in this structure, all the formal charges are 0. But in this structure, carbon is still 0. 1, 2, 3, 4. 4 minus 4 is 0. But here we have 6 and 6. 1, 2, 3, 4, 5, 6, 7 equals minus 1. And this one is 1, 2, 3, 4, 5. This is a plus 1. So we have a plus 1, 0, minus 1 versus a 0, 0, 0. This one is preferred. That's a better structure. Okay, one caution. When we calculate formal charges, these are not actual charges. We're not saying that oxygen had a minus 1 charge on it on one side and a plus 1 charge on the other side. This is a bookkeeping scheme, right? Just like the other method. It's just a way of tracking electrons. Actually, what did I just tell you? Oxidation states. Oxidation states are a way of tracking electron movement. In this case, the formal charge is the objective there is determine which Lewis structure is best. Okay, so now what we're going to do is, now we know how to write Lewis dot structures. We're going to use those structures in this model, the VSEPR model, valence shell electron pair repulsion. All that means is, let's take it from the end of the acronym and work our way backwards. Repulsion. We're going to watch the electrons in the bonds and the non-bonded electrons, and we know they're going to repel one another. That's the theory. They're in the bonds or they're not in the bonds, and they repel one another. So what we want is to minimize the amount of force amongst them. So we try to spread them out so that they're equidistant from each other in a regular geometric shape so that we minimize repulsions. electron pair repulsion. That's what we're talking about there. Those electrons are located in the valence shell of the atoms. Right? So even though they're bonded, we're saying they're bonded like water. These electrons are in valence shells, and they're repelling one another. So we want to position them in such a way that they minimize repulsions. That's the whole concept behind VSEPR. And this is part of the localized electron model. And it's used to predict the geometry of the molecule. Okay, so we need a list of regular structures that will fit with a certain number of electron pairs, bonded or non-bonded, in surrounding a central atom. We're going to take simple structures first. So one central atom, and then we have lone pairs and bonded atoms around it. Okay. Just know that when you have large molecules, you can have several centers of geometry. In other words, you can have one geometry around this atom, you can have another geometry around that atom. So for large molecules, you can have multiple geometries around various central atoms. Right? We'll get there eventually, but right now we're going to keep it real simple. Okay. So I find it useful to set up a chart. So how many number of electron pairs? Actually, it works better if we work in terms of groups, and I'll explain why that is. And then we want the electronic geometry. Okay, it will work from there to molecular geometry. Okay, so around the central atom, suppose you have, well, it's a no-brainer. If you have a single pair between, right? One pair or one group between. Let's see, let's use examples here. Examples. Right? If you have, oh, here's a good one. Right. Well, in this case, all right. Actually, I've got two centers here. Right? You can look at it this way. Around that central atom, how many groups do you have? You have one lone pair, and you have this triple bond. That's why I say groups rather than pairs. Because if they're in the same bonding between two atoms, I count them as a single. So here we have two pairs, two groups. If that's the case, then you have, it's always linear. This is as far away as it can get from these guys right here. That's linear. Okay. And if you looked at the other side, it would be linear also. Let's see. If we had three, let's use boron trifluoride. And we're going to have that. And this way, this way, this way, and just two here, two here. Okay, if you have three groups around the central atom, that is trigonal planar. It forms an isosceles triangle. We've got it drawn here like a T, but it's really trigonal planar. Maybe I should do that. The actual geometry would be like that, like this. Okay, trigonal planar. We'll get to the molecular geometry in a minute. This is electronic geometry. If you have 4 groups, for instance, methane. Right, 1, 2, 3, 4. That is tetrahedral. That maximizes the distance between these electron bonding groups. If you have 5, now you've got another, let's see, I'm trying to think. How about phosphorus pentachloride? 1, 2, 3, 4, 5. I'm not going to draw on the electrons because there are no lone pairs around phosphorus, so this works okay. If you have 5, then the best way to arrange those is in a trigonal bipyramid. And that would look something like this. You would have this triangular shape here and phosphorus in the middle. And then up here, you would have a chlorine, and down here, you would have a chlorine. And then there'd be a chlorine on the triangle. Okay, that's a trigonal bipyramid. So you have a pyramid this way, like you connect here, here, and down to here. That would be a trigonal pyramid. Well, actually, it would be a tetrahedron. But if we connect the rest of them down here like that, you've got a pyramid on top of a pyramid with the bases together. That gives you room for 5. 1, 2, 3, 4, 5. Okay? And then if you have 6, that's as high as we're going to go. If you have 6, let's see. Trying to think of an example. Sulfur hexafluoride. That you would have an octahedron. So it's kind of like this one, only it has a square in the middle. And we have sulfur and, did I say sulfur hexafluoride? Yeah, sulfur. So we'd have a fluoride up here and a fluoride down here, and then a fluoride on each of the points of this square. And that would give you an octahedron. If you draw the regular shape, right, if you connect all these like that, you get a side here, 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 that's 4, and then 4 more on the bottom. So that's 8, octahedron. Now, if you happen to have a lone pair of electrons, say, for instance, here, if we have ammonia, we have hydrogen back here, hydrogen here, hydrogen here, and a lone pair up there, then you got 1, 2, 3, 4, just like this, and that's a tetrahedral electronic geometry. Okay? But if you cover up, if you want to know the molecular geometry, then you don't consider the lone pairs. And now you have a trigonal pyramid. And a trigonal pyramid is due to one lone pair from a tetrahedral electronic structure. Okay? If you have 2 lone pairs, like water, like that, 1, 2, 3, 4. So that's a tetrahedral electronic structure. Cover up these lone pairs, what do you get? You get a bent molecule. That's it. 2 lone pairs from a tetrahedral is bent. If you have a trigonal planar, I can't think of an example right now, but if you have a lone pair over here and these 2 right here, one lone pair, then you have another bent molecule. Okay. Let's see. I may be stealing some of my own thunder. Angles. Okay. What's the angle for something like this? 180 degrees, right? Or that's bond angle. How about this one? 120 degrees, right? 120, 120, 120 is 360 all the way around. How about this one? Well, tetrahedral is kind of funny. The bond angle in a tetrahedral is 109.5 degrees for a perfect tetrahedron where there are no lone pairs. When you have a lone pair, what happens is that lone pair is not bound, it's not confined into a bond. So they tend to balloon. So this ballooning lone pair puts pressure on these other three. It pushes them down. So their bond angle, the bond angle here, would be less than 109.5. It's about 107. But theoretically, the bond angle in a tetrahedron is 109.5. How about a trigonal bipyramid? Well, if there are no lone pairs, then what do you got? Well, you got a bond angle between this one and this one right there. That's on a triangle, right? 120 degrees. But if you go from this one to that one, it's like here, here. That's 90 degrees. Okay? Or if you go from this one to here, that's 180 degrees. So you can have three different bond angles in a trigonal pyramid if there are no lone pairs. How about an octahedron? What are your bond angles there? Right? Right, well, that's 4 around in a circle. 4 times 90 is 360. So this is a 90 degree right angle. This one is a 90 degree. And this one is 180 degrees. Okay, so those are your possible bond angles. We'll talk about what if you have lone pairs in this arrangement or in this arrangement. I think I've got slides for that one. Let's see. Okay, so those are the general rules for using the VSEP-MAR model. And that's linear, right? We drew that one before. That's the only possibility for that one is 180 degree bond angle. With carbon in the middle as the apex, the central atom is the apex of your angle. pH 3, that's a trigonal pyramid. Why? Because it's like ammonia. Phosphorus has a lone pair up here. So it's tetrahedral, but we're missing one. So the molecular geometry is trigonal pyramid. And SF4 is a seesaw, SF4. Okay, let's do that one. SF4. Okay, sulfur has six electrons. Then we have 4 times 7. So 28 and 6 is 34. 34 electrons. Okay, sulfur's in the middle. We got fluorine, 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 2, 4, 6, 8. All right, so that's 26 electrons. So 6 times 4 is 24, right? If we do 6 more around each one to give them octets. 24. So that's 2. So now that sulfur has to have 2 electrons there. Okay, so what's the electronic structure? 1, 2, 3, 4, 5. 5 groups, trigonal pyramid, trigonal bipyramid. All right, so if we have sulfur in the middle and we put this triangle here, and then we have something up here and we have something down here. The question is, Where does the lone pair go? Well, we have to rely on research to tell us that one. What we find is that the lone pair, rather than being on here like this, is on one of these in the triangle. So the rest of them, fluorine, 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 and fluorine, go in those positions. So now this is the shape. This is a shape, but these are not bonds. Well, this is a bond, but these are not bonds. The bond is between here, 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 and here. So what do you get? Well, when you cover that up, you get a molecule that looks like this. Let's see. This. Because the lone pair is over here. Fluorine, 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 fluorine. So that's why it looks like a seesaw, right? There's the what do you call it? The fulcrum, and there's your seesaw. Okay. And the bond angles are 180 degrees here, and between this one comes up here, here is 90 degrees. Those are the only two bond angles in that model. It kind of twists your head around, doesn't it? Trying to visualize these. It probably would help if I had some models for you to play with. Let me see, I better leave that there for now. How about ozone? Well, ozone is bent because it looks like this. Excuse me. It looks like ozone. Yeah. Ozone is more like this, 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 this. Actually, I think it's got a double bond. 1, 2, 3 is 18. 2, 4 is 14. 2, 4, 6, 8, 10, 12, 14. All right. So now we need to take these two and make a double bond. Okay, so that's where you get the bent. So you have 1, 2, 3, which makes a trigonal planar electronic. And then when you cover up the lone pair, you get a bent, and this is 120 degrees. That's ozone. All right. Krypton tetrafluoride. When you draw that one, you get an octahedron electronic structure. Because you get krypton here, and you get this square here with fluorine, fluorine. And each of those fluorines has an octet. But you also get a lone pair up here and a lone pair down there. So when you cover those up, you get a square planar molecule. And we know this is true because research has proven it. We've done various types of tests, and that is the model for krypton tetrafluoride. Okay, a molecule that has polar bonds will always be polar. Is that true or false? That's a big F. It's false. It won't always be polar, because if the polar bonds are positioned in such a way that they're equal and opposite one another, or in a regular arrangement, then they will cancel one another out. For instance, methane, right? These hydrogens positioned around the carbon. Actually, a better example would be carbon tetrachloride. You ever heard of that one? It used to be called dry cleaning fluid, right? You go to the dry cleaner, and they put your clothes in a big stainless steel drum, and they pour carbon tetrachloride on it. And it dissolves. It's nonpolar. It dissolves all the oils and all the dirt out of your clothes. Doesn't damage the fibers. And then when you pull your clothes out, once you release the pressure, then all the carbon tetrachloride comes out as a gas. They don't let you do that anymore because it's hazardous. But once you position these chlorines around that carbon, you get a tetrahedral structure. And the bonds are all polar, but they're positioned regularly around this tetrahedron. They cancel one another out. So that's why carbon tetrachloride is nonpolar, and it's effective as a grease solvent. Now they have to use something more expensive. Okay. Carbon dioxide does contain polar bonds, but it's not polar, right? Because carbon dioxide is a linear molecule. Right? Cancels out the polarity of the bonds. So what we're trying to do is use geometry now, along with polarity of bonds, to determine whether the molecule is polar. Lewis structure for a xenon tetrafluoride, that's like the krypton tetrafluoride we did before. It's going to be square planar. Okay, so So if here are pictures of what I just put on the board, right? If it's a linear molecule, we're talking about the arrangement of electrons around the central atom. Trigonal planar 3. This is only electronic structure. This slide has not gotten to molecular structure yet. Now, if we have electronic structure plus atoms in the bonds, but we have some lone pairs. So here's a tetrahedron example, right? Trigonal pyramid, if you're one lone pair, that's that middle one. And then if you have two lone pairs, the molecules bend, or they say V-shaped. Some textbooks say angular. I like bend. Here we have trigonal bipyramid, and first lone pair, let's see. First lone pair gives you a seesaw. Second lone pair gives you T-shape. So both of those lone pairs are on the central triangle. So that gives you a T-shape, molecular shape. And of course, if you have three lone pairs, you get a linear molecule. Okay. Let's see. When phosphorus reacts with excess chlorine gas, you get phosphorus pentachloride. In the gaseous liquid states, this substance. Oh, okay. This is a good one. I guess I'm going to have to erase some stuff here. See what I can get away with without erasing all of it. In a gaseous state, you have two different forms. You have PCl4 plus and PCl6 minus. What's the geometry of each of these? You have a mix, actually. PCl5 neutral, PCl4 plus, and PCl6 minus. So let's do the PCl5 first. Right. Phosphorus is 5. This is 7 times 5, which is 35, 40. 40 electrons. So we have a phosphorus. We have 1, 2, 3, 4, 5. Chlorine, 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 chlorine. So 1, 2, 3, 4, 5 times 2 is 10. 2, 4, 6, 8, 10. What would we say, 40? So we have 30 electrons left. So if we put 6 around each one of these, 6 times 5 is 30. So we're all used up. So this, with 5, we get a trigonal bipyramid. So this one is trigonal bipyramid. Okay. How about PCl4 plus? PCl4 plus charge. Okay, we got 5 for that one, and we got 4 times 7 for this one, which is 28. 28, 3 is 31. No, 28, 5, excuse me. 28, 5 is 33. 33 electrons. Okay, for this one we have phosphorus, and then 1, 2, 3, 4 chlorines. So 2, 4, 6, 8 is 25 electrons. 6 times 4 would be 24 more electrons that we can that, and we have 1 here. Okay. Oh, we don't have 1 there, did we? That plus charge. This is 24 because we had -1. So we don't have 1. That's our structure. So this one is tetrahedral. Okay. How about PCl6 minus? PCl6 minus. So we have 5, and 6 times 7 is 42, so that's 47, correct? Plus 1 for this one right here. So it's 48 electrons. So 1, 2, 3, 4, 5, 6. 2, 4, 6, 8, 10, 12. So that's 36. 2, 4, 6. 6 times 6 is 36. And for these 6 chlorines, we can put 6 more around them and have an octet. So that's gone. So this structure is 6, which is octahedral. Right? And we should write it this way. When you write the Lewis structure, you have to put the charge. So this one would be plus, and that one would be neutral. Okay. So PCl5 is trigonal bipyramid. All right. And PCl4 plus here should be tetrahedral. Here we go. Notice they've got it in brackets with a plus sign. And the last one should be octahedral. There we go, with a negative sign. Okay. Let's see. How much time do I have? 3:50. Okay. Yeah, we got time. Noble gases have filled S&P valence orbitals. They're not expected to be chemically reactive, but we have forced them to react in some cases. In 1960s, several of them, the krypton, xenon, and radon, were synthesized compounds. So notice that the ones that form the compounds are down here: krypton, xenon, radon. Argon, neon, and helium, they're not going to go for it. And largely due to the fact that while argon does have available d orbitals, it doesn't want to use them. But krypton is okay with d orbitals, xenon, okay, radon. They'll use their d orbitals to form bonds. Plus, the electrons are very far from the center, so they're a little more loosely bound. Okay, xenon tetrafluoride. What's the structure? And does it have a dipole moment? Right. Xenon tetrafluoride. So we have 8 electrons here. We have 4 times 7 is 28. So that's 36 electrons. Xenon in the middle. And let's see, fluorine, 2, 4, 6, 8 would be 28, right? 2, 4, 6. So 6 times 4 for the fluorines to complete their octets is 24. So we have 4 electrons left, 2 here and 2 here. So the electronic structure is 1, 2, 3, 4, 5, 6, or octahedral. But these two sit above and below the square. So these fluorines are in a square plane for the molecular geometry. There you go. So there's the Lewis dot structure. And there's their arrangement, the electronic arrangement. Right. Now we need to look at where are those non-bonding pairs. All right, if we put them, this just speculates. If we put those non-bonding pairs here on the square, they're very close together. Right, that's too much repulsion because they kind of balloon out. But if we put one up here and one down here, they're still 90 degrees away from their neighbors. They're bonded pair, the bonded pairs, yes. But they're far away from their ballooning neighbors. So logically, we would expect them to be at the apexes of the octahedron and leave the fluorines in the square. And that's what we see. Experimentally, we see that. Let's see. Let's see. That's just an explanation. Square planar is a molecular structure. Okay. Oh, and polarity. Okay. You got 2 lone pairs this way, but you've got equal fluorine xenon bonds out this way, and they all cancel each other out. Even though fluorine is more electronegative than xenon, you have them regularly spaced around each other, and the vector sum is 0. No dipole moment. That's it. Yay! So we'll come back Thursday and talk about this lab, the Dumas method for determining molar mass of a volatile liquid. That's a fun lab. I think you'll like it.